Welcome to this lecture on dyadic data analysis and structural equation modeling. In this lecture today, I'm going to go over how to conduct dyadic analyses in M+, and what APIM, or the Actor-Partner Interdependence Model, is, along with its associated challenges and unique pieces that we need to work through when we're doing this. As couple and family therapist researchers, we are ultimately concerned with systemic interaction. So we really want to know more about how one person can influence or affect behavior in another person, and also what we can do as therapists to intervene to help in those relationships. So ultimately, what we want to know about is what happens between people within a system. So we want to know about couples, about parents and children, about therapists and clients. We want to know about dyads within a system as researchers. So consequently, simply doing individual research with one person oftentimes does not get at the kinds of questions we are really interested in as systemic researchers. And because of that, systemic data analyses, or dyadic analyses, is at the very heart of doing systemic researcher. So dyadic analyses are a type of data analysis. It is the type of data analysis where we do this. And I'm going to introduce you to this today because a lot of MFTs do dyadic analyses in their research, and it's a very important part of the research that we do. So the Actor-Partner Interdependence Model, or APIM, is the name of the model that is what we call dyadic analysis, the name of the specific kind of analysis that we do with dyadic analyses. So in APIM, you have two pieces, an actor and a partner. Those are the two people. The actor, or what we call actor effects, are the effects of somebody on themselves. So the actor effects are pretty much what we do with every other kind of research. It's the research about people, independent and dependent variables. So an independent variable about themselves, dependent variable about themselves. The partner effects, however, are the effects going from one person to another person, or from an actor to a partner, or from a partner to an actor. So within this, what we are really doing is looking at the interaction of variables onto their own self, and then also onto another person within their system, onto the other person in the dyad. In order to do this, we need data that has an identifying dyad variable. For example, you may have a variable that's a couple ID or a family ID, but you need some kind of ID variable that connects the two people in the system so that we can distinguish those dyads apart from the individuals. And then we also need to make sure that the people in those dyads are asked the same questions so that we can have the corresponding variables for each person in the dyad when we are doing our analyses. So in our analysis, we're going to have actor effects and partner effects. Both people, both our actor and our partner, so both people in our dyad are going to have actor effects and partner effects. An actor effect is the effect of a person's X variable on that person's Y variable, so their IV on their DV. Both members of the dyad have an actor effect. A partner effect, on the other hand, is the effect of a partner's X variable on the person's Y variable, or the person's X variable on the partner's Y variable. Both members of the dyad have a partner effect. So a basic APIM model looks like this here, where we have the patient's depression on the patient's quality of life, and also the patient, and that's an actor effect, and also the patient's depression on the spouse's quality of life, and that's a partner effect. Just like we have the spouse's depression on the spouse's quality of life, actor effect, and the spouse's depression on the spouse's patient quality of life, or the partner effect. So when we do this, what you will essentially see here is we have the same model reproduced for each person in the dyad. So we'll have the model, which this one's a pretty, again, a basic simple model with one IV and one DV, and then we're reproducing it for each partner in the dyad. We have the patient and the spouse in this case. When we are asking questions, because of that, when we're asking our research questions, we essentially have our research question broken up into two sections. We have the actor and the partner effects. And when you're writing up your research questions, you can organize them in this way, your actor effects and your partner effects. So take your basic research question that you have, and then you ask it once about, you phrase it in the way of an actor effect, so on their own, and then you ask it again as a partner effect, so on their partners. So in the example I have here for you, this is actually from my dissertation. You can see I have two main questions. I'm curious about acceptability for online boundary crossing and how that is associated with partner intrusion, relationship satisfaction, and perceived responsiveness. And then I'm also asking about intrusion and how that's associated with relationship satisfaction and partner responsiveness. So I ask it in the actor effects way, where you can see everything here in black is the exact same between actor and partners, and the only words that change here are those in blue, where I change it from with their own reports for the actor effects to the partner effects with their partners' reports. So that way I really have two research questions, but because I'm doing an APIM model, I'm asking it asking about it for the actor effects and then asking it again for the partner effects, which gives me a total of 4 research questions. When conducting an actor-partner interdependence model, there are 2 main issues that we need to deal with before we run our model. The first is distinguishability, and the second is non-independence. I'm going to talk about non-independence first, as that is the simpler of the 2 to deal with. So non-independence. This is all about that basic assumption of independence we talked about back in advanced statistics and multivariate, that parametric statistics have an assumption of independence, which is that our responses from our participants in our study are not significantly associated with responses of other participants in our study or in our sample. Now, when we're doing dyadic analyses, we are violating the assumption of independence, because we are assuming and hoping for the responses for one person in a dyad is significantly associated with the responses in the other person in the dyad, which means that half of our participants' responses are influencing the other half of our participants' responses. This violates independence. So because of this, we need to evaluate the level of non-independence. We need to deal with this, and then we also need to make sure that we deal with the issue of power that comes with this. So the main way that we deal with this issue of non-independence is that we make the dyad, or the couple, the unit of analysis rather than the participant. When we do this, essentially what we're doing is then maintaining the issue, or maintaining the assumption of independence, because each dyad is independent from each other dyad. So each dyad is independent, therefore maintaining independence. And the way we do this is making the dyad the unit of analysis. That's why we restructure our data. One of the primary reasons we restructure our data into dyadic analysis, which I'm going to get to at the end of this lecture. So when we do this, though, we are reducing our sample size by half. If we have 100 individuals, we have 50 couples, which means 50 becomes our unit of analysis and also our sample size. And this creates some unique issues around power. So because we are making n, the number of n is assumed to be the number of independent observations, which in dyadic analysis is really our dyad, or a couple rather than an individual, we need to kind of take a look at this. So one way we do this is by looking at the correlations of these variables within the dyad, or the correlations of these 2 variables. So we'll take the same measure for both people in our dyad. The example I'm going to show you here is between husbands and wives, and we look at the association between the same item on husbands and wives and look at that correlation. The larger the correlation, the smaller the effective n that we have in our sample. So this here shows you, illustrates this a little bit more clearly, that, like, say we have 100 individuals, which means we have 50 couples. If the association, the correlation between husbands and wives on these variables is 0, meaning there is absolutely no association whatsoever, we really have 100 independent observations. If the correlation is 0.5, Our effective n really means we have 75 independent observations. And if our correlation is 1, then we effectively have 50 independent observations because we have the only independent observations there are at the couple level, the dyadic level. This comes from Kenny and Cook's book. They have an entire book on doing APIM. And if you end up doing a lot of actor or dyadic analyses, I really suggest you get that book because it covers these issues in a lot more depth, and we're kind of scratching the surface today. So in order to really make sure that you properly assess your non-independence, Kenny, Cashy, and Cook really recommend that you always report your correlations and always do your correlations so that you can assess that and really evaluate your power level with that. So to do that, you just go to correlations. You may need to make sure that you control for certain variables when you do that. If you do that, you go to the partial correlations. And when you do that, you can input what you're controlling for. So in this example here, we're looking at husbands and wives relationship quality while controlling for their years married so that we can then get the controlled correlation between those two. So in this case, it's 0.62 or 0.619 is the correlation between husband and wives for relationship quality. Now, these next slides, I'm going to kind of show you a little bit about what we do with that correlation value. So because we have non-independence, and we will often have non-independence, we're really never going to have a correlation of 0, which means our effective n is smaller than our individual sample size, which is again why we often use the dyad as our sample size. From that, we have two questions. One, if the data are non-independent, will we be able to detect a small, a medium, a large effect size? What kind of effect are we going to be able to detect? And our second question is, how much power in our key tests of independent variables is gained or lost when we use the dyad as the unit of analysis rather than the individual? So in Kenny's book on actor-partner independence modeling, they have some tables in the book that help you to assess these, and I have these copied in these next slides. So this slide here shows us how we can address that first question. And again, that first question is, if the data are non-independent, will we be able to detect a small, medium, or large effect size? So in other words, how many dyads do we need in order to detect an effect size, a small, medium, or large effect size in here? So this table is from Kenny, Cashy's, and Cook's book on APIM. So in this, it tells you the absolute value of the population correlation that you would be able to detect. So, let's take a look at, like, if we had 80 couples, which is where that red line is there. So if we have 80 couples in our analysis, our power is 0.14 for detecting a small effect, 0.78 for a medium effect, and we have plenty of power, which is why there's an asterisk there, for detecting a large effect in the population. Or if we had 200 couples, it would be 0.29 for a small one, 0.99 for a medium effect size, and plenty for a large effect size. Now the second question is, what are the ramifications for the power of the test of the independent variable when the dyad rather than the person is used as the unit of analysis? So again, this is a table taken from their book. And so the power to detect an effect size of 0.5, which is where this red arrow is here, is 70 for the independent individual's design. So if we had, I'm looking at just the independent individuals in that, but if we wanted to have if we had a correlation or wanted an interclass correlation of 0.25, we would need 59 couples in order to be able to detect that. So when the interclass correlation is very small or close to 0, there's little loss in power. So you can see, for example, we have in the 0.1, so the small effect, we have 7 individuals, and at 0 we have 7 couples. Or at like the 0.5 level, we have 70 individuals and then 69 couples or dyads. So the main point or takeaway from here is that as the interclass correlation increases, so as that correlation between our dyads increases, power is lost, since it means less is gained by assessing both partners. So the main issue with non-independence, to kind of summarize this together, is that when we are doing dyadic analyses, we are violating our assumption of independence, and therefore we are losing our total effective N. So it's not really that we have as many independent observations as we think we do. The main way to get around this is to make sure that we are using the dyad as our unit of analysis rather than the individual. And Kenny and Cashy and Cook's book on APIM goes into a lot more detail in this, and they have some great tables that kind of help you to understand how many couples you need in order to be able to detect small, large, and medium effect sizes, and also to understand why power becomes bigger of an issue when that correlation between our partners is stronger. The second issue is distinguishability. So distinguishability is all about whether or not you can tell the difference between an actor and a partner in a sample. So can you tell the two people apart in your dyad? There are two kinds of distinguishability that we talk about. There's theoretical or practical and empirical. The theoretical or practical distinguishability is all about whether you can actually determine that the two people are different from each other. So theoretically distinguishable dyads have a meaningful factor that can be used to order the two people apart. So in same-sex research, this would be gender or the sex of the couple. So men and women, husbands and wives. In clinical research, we have patient, or we may have client and therapist and client. Or we may have in some more other research, we may have like patient and caregiver and child and caregiver. We may use race when we're doing mixed race dyad analyses. But we have some factor, some meaningful factor that distinguishes the two people apart. In theoretically non-distinguishing samples, we do not have a meaningful factor. So when we're doing same-sex couple research, we may not have a meaningful factor that distinguishes the man from the man, the woman from the woman in these kind of dyadic analyses. In traditional actor-partner research, we have actor and partner or anchor and partner, where the anchor is the first person to respond and the partner is the second person to respond in the dyad. There's no meaningful way to determine the difference between the actor and the partner. The main issue in non-distinguishable dyads is that you can reorder them in different ways and get different responses because the factor that's distinguishing them is not meaningful in any significant way. So preferably when we're doing dyadic analyses, we want to have a theoretically distinguishable factor or a meaningful factor that can create a theoretically distinguishable dyad. However, even if we do not have a distinguishable factor, we can still do our analyses. The bigger issue in distinguishability is not theoretical, but empirical distinguishability. So empirical distinguishability is really about whether or not each individual's scores on measures are significantly different from the other person in the dyad. So is the anchor distinguishable from the partner, or the husband from wife, patient from caregiver? Are these two people, and are their scores, their responses on these measures significantly different one from another? If they are not significantly different, what that means is that the actor and the partner have no difference between them. It doesn't matter, or wouldn't really make any sense to do an APIM model because you won't find any differences. So in order to evaluate whether there's distinguishability, we have to conduct a test. And what we're going to do is conduct the omnibus test of distinguishability. What essentially we're looking for in this test is to determine whether or not there are any significant differences within the dyad or between the dyad in the analysis. If there are no significant differences between one person and the other person in each dyad, then they are not distinguishable. If there are significant differences, then they are distinguishable. So an omnibus test is any kind of statistical test that examines a number of alternatives at once. In this case, we're doing an omnibus test of distinguishability. So we're going to do several tests at once, or we're going to do a test to determine whether or not the couple or the dyad is empirically different, or in other words, distinguishable from each other. When we're doing this, there are 6 pairs of parameters that we can look at to determine whether there are differences. And so what we can do is look at each pair of corresponding parameters for the actor effects, for the partner effects, the means, the variances, and the y-intercepts and the x variances. So the y is going to be our dependent variable and the x is going to be our independent variable here. So to conduct an omnibus test of distinguishability, you're going to do 3 steps. The first step is to run the fully unconstrained model. So just run the model as is. And then the second step, we're going to constrain the model. Now to do a true omnibus test of distinguishability, we would constrain each pair of parameters for all 6 of those. So we'll constrain all of the actor effects, all the partner effects, all the means, error, variances, y-intercepts, and variances. However, in reality, you don't really need to do all 6 of those because if any of them are distinguishable, we can evaluate. And really the ones we're most interested in is the means and the paths or the effects. So typically when you do this, you really only need to test the actor effects, partner effects, and the means in order to find out if they are distinguishable. And ultimately, those are the effects we're most interested in. And so you can just do those. 1, to make your life a little bit easier, and 2, if the other pieces are not distinguishable, it's going to be much less meaningful to our analyses because we're really interested in those paths. So the third step is then doing a chi-square difference test. So we're going to test the difference between our unconstrained and our constrained model. If our model gets significantly worse, moving from the unconstrained to the constrained, it means that our pairs or our dyads are distinguishable. If it is not significant, then our pairs are indistinguishable or not distinguishable. So here I have an example, including the M+ syntax. This is actually my dissertation, so this is the same piece from those research questions I showed earlier. So hot tip for you, when I'm doing this, you'll see as I have in green, I use the notes feature in M+ in order to help organize and better organize my analyses and also to help organize my results. So I start with model and then I organize by my actor paths. And I'm going to break out between each person. So I have actor paths for men and actor paths for women because this is an opposite sex data analysis. And then I have my partner paths for men and partner paths for women. So in this, in the figure here, the blue lines are my partner paths and the black lines are my actor paths. So you can see I have the same model at the top and the bottom, and then I have the partner paths going between the 2 models, creating my APIM model. So what you can see here is I have CSI, that is the relationship satisfaction, that's the couple satisfaction index. RESP is responsiveness, intrusion is intrusion, and bound cross is boundary crossing. So I have my actor path syntax, so CSI on intrusion and boundary crossing, so relationship satisfaction on intrusion and boundary crossing. And when I set this up, this is going to be important because it's going to help me more easily do my constraint testing. I'm going to put each of my IVs here on a separate line. This is going to help me, and you'll see in the next slide how this helps me. So I have CSI on those 2, then I have partner responsiveness on the same 2, intrusion and crossing, and then I have intrusion on boundary crossing. So there's the men's, and then for the women, it's the same thing. It's just instead of M, it's F. And then my partner paths are going to do, I'm going to do the same thing as I did with my actor, but with my partner. So I'm going to have the men's CSI on women's intrusion and boundary crossing, men's responsiveness on intrusion and boundary crossing, and then men's intrusion on women's boundary crossing. And for the partner paths, I'm just going to switch the M's and the F's. So I have women's satisfaction on men's intrusion and boundary crossing, so I'm getting these 2 paths. And then same thing with responsiveness, where I'll get those two paths, and then intrusion, where I'll get that path there, which I just noticed I don't have on my model. So let me add that real quick for you. So now they're all on there. We have our 3 partner paths and our 3 actor paths for our IVs, and we have our 1 for each of our 2 for the mediating variable and 2 over here too. So here is the syntax for doing an APIM model where I have essentially four variables, 4 for men and then 4 for women, giving me 8 total variables in the actor partner. Now the next thing I need to do is actually run my constrained model. So I'm going to show you this in 2 steps. First, I'm going to constrain my actor and partner paths, and then I'm going to show you the syntax for constraining the means. So in this next slide here, I have the paths constrained, the corresponding paths. So to constrain a corresponding path, all you need to do is put in parentheses a letter. So you can see my men's satisfaction on intrusion. So men's satisfaction on their own intrusion here. And that is this letter A here. I'm going to constrain the same path, the same corresponding actor path for women. So I have the A next to the corresponding actor paths for men and women. And so you can see by me putting a line, each independent variable or each variable on a line, I can just go A, B, B, C, C, D, D, E, E. So you can see I have A, B, C, D, E, A, B, C, D, E. Because I've organized my syntax cleanly by having my actor paths for one partner, actor paths for the other partner. So in this case, actor paths for men, actor paths for women, and wrote out the same paths in the same order. And because I put each IV on its own line, I can simply go through and go A, B, C, D, E, A, B, C, D, E. And then for the partner paths, I did the same thing. I had the same corresponding paths on each line. So men's satisfaction onto women's intrusion, women's satisfaction onto men's intrusion, and then boundary crossing, and then intrusion, and then boundary crossing again, and then the last one. So you can see I have A, B, C, D, E, A, B, C, D, E on the corresponding men's and women's actor paths, and then F, G, H, I, J, F, G, H, I, J on the corresponding partner paths. On the diagram, I put a few of the letters in here so you can see where those corresponding paths are, so that 2 A paths are both partner intrusion to relationship satisfaction for actors, and this G path here is the corresponding partner effect. So I'm going from one person's boundary crossing to the other person's relationship satisfaction, one person's boundary crossing to the other person's relationship satisfaction. And by putting the A next to those pairs, or that letter, I'm telling M+, constrain these 2 paths to be the same estimate. Make them the same. So in this way, what we're doing is determining whether these are actually distinguishable. Are these pairs of paths significantly different one from the other? To add in the mean constraints then, you would just, again, I'm going to put my mean constraints here, starting with the exclamation point so I can have a note for myself here what this is about. And all you do there in order to constrain a mean is you put in brackets, the hard square brackets, the name of the variable, and then next to it in parentheses you put a value. So in this case, again, I'm going to constrain them to be equal to each other. So I'm going to do men's CSI, so that's men's satisfaction, being constrained equally to women's satisfaction. So 1 on 1. And then intrusion we have 2, and boundary crossing 3, and responsiveness 4, with a semicolon at the end of each line. So this syntax here then, I am constraining all of the corresponding actor and partner paths and the corresponding means to be equal to each other. So when I run this, I would grab my chi-square and it also assess the model fit of each of these models. So when I run this, let's go to next. There we go, next slide. So when I ran this, I found that the fully unconstrained model had a chi-squared of 4.064, 4 degrees of freedom, and a p-value that was non-significant at 0.397. And I didn't include this here, but my model fit looked pretty good. It was a really good model fit, and I was really happy with it. When I ran the fully constrained model, so that's this model on this previous slide, I get a chi-square value of 540.086, 32 degrees of freedom, and P is less than 0.001. So I just see 0.00 in the output. And my model fit gets pretty bad for the other pieces in there. So I'm already thinking I'm going to be pretty good showing distinguishable dyads. But to complete it, I do the chi-square difference test. So 540.086 minus 4.064 gives us 536.022. 32 minus 4 gives us 28 degrees of freedom. And when I put that into a chi-squared p-value calculator, I see that the p-value is less than 0.001. This tells me I can then conclude that the model got significantly worse, and therefore the dyads are distinguishable, and I can proceed with my analysis. In my write-up for my paper, what I wrote for this, and this is from my actual paper that I wrote from this analysis, is prior to selecting the final model, an omnibus test of distinguishability was conducted and demonstrated that men and women were empirically distinguishable. Therefore, the model could be evaluated without equality constraints. And I cite in here the Olson and Kenny article that talked about doing this. So that's how you write it up, and that's how you do the omnibus test of distinguishability. So in summary, there are two main issues that we have to address when we're doing dyadic analyses or running the APIM model. The first is distinguishability. We have theoretical and empirical distinguishability. And theoretical distinguishability is all about whether there is a meaningful factor that separates each partner in each of our dyads. Empirical distinguishability is about whether you can actually get an empirical difference between each person. So are their scores or their responses significantly different one from another person? And are the relationships between these variables significantly different one from another person? We do this by doing equality constraints. The most straightforward way to do this is to constrain the corresponding actor and partner paths as well as the means, and then do a chi-square difference test between the unconstrained and the constrained model. If that chi-square difference test is significant, it means that your model got significantly worse, and they are empirically distinguishable dyads, and then you can proceed with your analysis. The second main issue is non-independence. Because half of our sample is significantly related to the other half, we need to make sure that we are using the couple rather than the individual as our unit of analysis. And in order to address the issue of non-independence, we can look at the correlations between each of our people in the dyads to evaluate how many couples we need in order to detect small, medium, or large sample sizes. And we can also see how our sample size is affected by looking at those tables that Kenny. So along with that, because we want to make sure that we're analyzing the couple as our unit of analysis rather than the individual, we're going to restructure our data into dyads. If you're using a data set that has already done this for you, congratulations, you can skip this part when you're doing your own paper. But pay attention to this because you're going to need it if you keep doing dyadic analyses, because very rarely is it set in dyadic structure. So to do this, you need to know two things. You need to know the unique participant ID, and you need to know the unique dyad ID. And then you need to know that meaningful factor that's going to distinguish the two people in that dyad, whether that's gender, whether that's role, like parent-child, whether that's age with older and younger siblings, whatever that meaningful factor is, you need to have one of those. If it's whoever responded first or second, you need to know what that factor is, otherwise you're not going to be able to create dyadic structure. So when you're creating it, you need to, what we're essentially going to be doing is moving one participant per line to having the couple on one line. And we're going to separate out each of their responses by saying, like with satisfaction, it'll be like satisfaction point 1, satisfaction point 2. So we have the separation of those two variables between each person. So the first step on this is identifying your variables for the participant ID, your dyad ID, and your dyadic, your meaningful variable that distinguishes the two of them. The next thing you're going to do is make sure that you sort your data. You want to sort it by your participant ID first, and then your dyadic ID second. The third piece then is to run your syntax for restructuring your data, and that's going to be here on the next slide. It's a pretty simple and short syntax in order to do this. So here is the syntax for creating dyadic structure. The first line I have here, sort cases by participant ID, couple ID, is the syntax to actually sort your file, just in case you forgot to do it, or to double check that you actually made sure you do it. So participant ID, you'd actually put the name of the variable, that's your participant ID name, and then couple ID would be the actual name of the dyadic, whatever the name of the variable is for that like couple or family, the ID for each dyad. Factor in here in the syntax would be the name of whatever factor it is that you have, that meaningful separation factor. So for example, if like my participant ID was just called part ID, I would have sort cases by part ID, and if couple ID was like fam, so I'd say sort cases by part ID fam period. Cases to vars ID equals, and then you're going to put in the ID, the couple ID here, so I'd put like fam here, and then index equals, that's going to be your uniquely separating factor. So you have index equals and the name of your factor. So if it was, for example, sex or gender, if it was called sex, I'd put sex. And then group by equals index. So it's going to group by that index, that variable over in the index. So when you do this, what it's actually going to do is it'll take the couples and put them all on the same line and separate them by that unique factor. And it's going to put a 0.1 next to the first, whatever that factor is. So if it was sex and men, in this example, women equals 1 and men equals 2, it'll put a 0.1 next to all the variable names for women and a 0.2 next to those same variable names for men. So in other words, like satisfaction becomes satisfaction 0.1 for women and satisfaction 0.2 for men. It'll be organized so all the 0.1s will be first, and then all the 0.2s will be next in the list in your data set. Essentially, what will happen is you will double the number of variables in your data set, because you're now going to have all the variables for men and all the variables for women, or all the variables for one partner and another partner. So M+ doesn't like the points in those variable names. So when you're doing those variable names, now you can leave them in SPSS as they are, because remember we're going to take off those variable names anyways when we save our file. However, I like to have my SPSS file all set to go so I can just copy and paste really easily. So to do that, you can highlight the list of all your variable names in SPSS, copy them, open up a Word document, paste them all in there, and then just do a little Control F or Control H, and that way you do your copy and replace, and put 0.1 and replace that with -W, and then replace 0.2 with -M. The other reason I like to do this in SPSS is I don't always remember what the 0.1 and 0.2 was. I don't remember if 0.1 was women or men, so I'd rather just have it in there so I can remember, and I don't have, it can be right there and I don't have to remember which is which. And once you've done that, you have now created a fully dyadic structure to your data, and you're ready to conduct a structural equation model. In our next module, I'm going to show you a full example of conducting an APIM, an actor-partner interdependence model. So we're going to go from beginning to end of creating dyadic structure, of testing distinguishability, and then conducting an APIM model with constraint testing.